Hi everyone! This is Professor M. Does Science, and today I want to talk about coherent states of the quantum harmonic oscillator in another one of our videos on rigorous quantum mechanics. Coherent states are defined as the eigenstates of the lowering operator. Today we'll look at two fundamental properties of coherent states. The first is what they look like when we write them in the energy basis, and the second one is the time evolution. This will prepare us to study the hugely important role that coherent states play in quantum mechanics, and you will be able to find a full series of videos by following the links in the description. As a teaser, coherent states are the states that most closely resemble the classical motion of a harmonic oscillator, and they also play a key role in the quantum theory of light. So let's go! Our focus today is on the coherent states of the quantum harmonic oscillator, so let's start with a quick refresher of this very important system. The Hamiltonian H of the quantum harmonic oscillator has a kinetic energy term and a potential energy term that is proportional to the position squared. We can also write down this Hamiltonian in terms of the ladder operators A dagger and A, or in terms of the number operator n. This is the eigenvalue equation of the Hamiltonian, where as usual these are the eigenvalues and these are the eigenstates. The eigenvalues are equal to h bar omega times n plus 1 over 2, where n is a non-negative integer, 0, 1, 2, and so on. So today we will mostly work with the ladder operators, the lowering operator A and the raising operator A dagger. The ladder operators allow us to move between eigenstates, and to see this more clearly, let's draw the real axis and place some of the allowed energy eigenvalues on it. Each of these is associated with a corresponding energy eigenstate. Acting with the lowering operator on eigenstate n gives a new term that is proportional to eigenstate n minus 1, and the energy of the state has decreased by 1 quantum h bar omega. Conversely, the raising operator acts on eigenstate n to give a new term proportional to eigenstate n plus 1, raising the energy of the state by 1 quantum. So this is our refresher on the quantum harmonic oscillator, but you can follow the links in the description for all the details behind these concepts. Okay, so we're now ready to define a coherent state. Coherent states feature in a variety of areas, and those associated with the quantum harmonic oscillator are sometimes called canonical coherent states to distinguish them from the others. I'm going to use the simpler term coherent states, but just be aware that you might find this slightly different terminology in the literature. Okay, so a coherent state alpha is defined as an eigenstate of the lowering operator. In this expression, this is the eigenvalue, and this is the eigenstate. As the lowering operator is not a Hermitian operator, alpha is in general a complex number. What does it mean conceptually that coherent states are eigenstates of the lowering operator? An eigenstate is a special state which doesn't really change when you apply the corresponding operator. All that happens is that you may get a scaling factor, the eigenvalue. But remember that the application of the lowering operator on an energy eigenstate removes a quantum of energy. And so given this, it may appear somewhat strange that the lowering operator can have eigenstates at all, as removing quanta of energy should definitely change a quantum state, right? Well, we will next build an explicit expression for a coherent state that will help us make sense of this. To do so, we will write the coherent state in the basis of eigenstates of the Hamiltonian. Let's write a general expression of a coherent state in terms of the energy eigenstates of the quantum harmonic oscillator. As usual, the expansion coefficients are given by the bracket between alpha and n, and I'm writing an explicit dependence on alpha to highlight that they may be different for different coherent states. Let's now consider the action of the lowering operator on the coherent state. Expanding the state in the energy basis, we get this. We can move the lowering operator inside the sum and obtain the sum over these terms. Now, remember from the video on ladder operators that for n larger than or equal to 1, the lowering operator acting on an energy eigenstate gives another energy eigenstate with one fewer energy quantum. And for n equals 0, the lowering operator acting on the energy eigenstate kills the state. Using these results, we can write that the action of the lowering operator on a coherent state is equal to a sum over the expansion coefficients, square root of n, and the energy eigenstate n minus 1. Note that the sum now starts at n equals 1 because we've killed the state at n equals 0. But n is just the index of the sum, so it is a dummy index and we can replace n by n plus 1. To conclude that A acting on alpha is equal to this expansion where the sum again starts at n equals 0. To continue with our derivation for an expression of a coherent state in the energy basis, we next need to remember that a coherent state is an eigenstate of the lowering operator. Then we can use this expression up here that we've just derived to rewrite the left-hand side like this. And the right-hand side is equal to the eigenvalue times the eigenstate, which I am also expanding in the energy basis. Moving all terms to the same side, we get sum over n of the term proportional to the n plus 1 coefficient and the term proportional to the n coefficient, all acting on the n eigenstate and all equal to 0. This will only be true if all terms in brackets vanish for any n, so that we get a recurrence relation for Cn plus 1 in terms of Cn. This relation is true for any n, so we can now iterate and write Cn in terms of Cn minus 1, and so on. We can rewrite this expression using the Cn coefficient as the starting point and iterating all the way to C0. We can combine these prefactors to this single term times C0. And we now have all the ingredients to write a coherent state in the energy basis. We can expand the coherent state with the standard expansion, and using the expression up here for the coefficient Cn in terms of the coefficient C0, we can then rewrite this expansion as a sum over n of these scalar factors times the corresponding energy eigenstate. This means that all we need to fully specify the coherent state in the energy basis is to determine the value of C0. As you may have guessed, we are going to use normalization to fix C0. We insist that 1 is equal to the sum over the absolute value square of the coefficients. And we can now insert the expression of the Cn coefficients in terms of the C0 coefficient. This term does not depend on n, so we can take it out of the sum, and we end up with this. This sum here is now the power series of the exponential of the absolute value of alpha squared. And we end up with the absolute value of C0 squared times the exponential. This means that the absolute value of C0 squared is equal to this exponential. To determine C0, we need to make a phase choice. The conventional choice is to make C0 real and positive, so we end up with this. And with this, we can now write the coherent state in the energy basis. Using this expression we derived up here, we can copy it to write that the coherent state can be expanded in the energy basis like this. We can then use this expression we just derived here for C0 to end up with an exponential factor multiplying the weighted sum over the energy eigenstates. And this is the final expression for a coherent state in the energy basis. So, what can we learn from this explicit expression for a coherent state? Again, remember that the eigenstate of an operator is a state that at most changes by a scaling factor when we apply the operator on it. a coherent state is an eigenstate of the lowering operator, which implies that the application of the lowering operator should not change the state apart from a simple scaling. But we know that the action of the lowering operator on an energy eigenstate removes an energy quantum. So how can we rationalize this? This coherent state up here is a superposition over all possible energy eigenstates, so essentially a superposition over an infinite number of energy eigenstates. When we act with the lowering operator on it, for every term in the sum, we remove one energy quantum, but the form of these expansion coefficients is such that every term becomes exactly equal to the original term with one fewer energy quantum, so that the overall state does not change. This is enabled by the fact that the sum is infinite, so there is no such thing as a highest energy state that we cannot recover after applying the lowering operator. Another interesting point to note is that coherent states are associated with the Poisson distribution. If we have a quantum harmonic oscillator in a coherent state, then the probability of measuring a particular energy level n is equal to the corresponding expansion coefficient squared. Using the expansion up here, we can insert the value of the expansion coefficient, and we can simplify this expression to this. This is indeed a Poisson distribution. And this property has important implications. For example, in the field of quantum optics, it means that coherent states of photons can be split into other independent coherent states, something that can only happen with Poisson statistics. But in this video, we're going to simply leave it as a neat observation and move on for now. Now that we understand coherent states, let's investigate their time evolution. The first step is to realize that the Hamiltonian of the quantum harmonic oscillator is time independent. And remember that a system for which the Hamiltonian is time independent is called a conservative system. From the video on the Schrödinger equation, we know how to evaluate the time dependence of a conservative system. So let's imagine that the initial state of our system, psi at time 0, is equal to a coherent state alpha 0. We can then write it in the basis of energy eigenstates, as we derived a moment ago. It is equal to this exponential prefactor times this infinite superposition of energy eigenstates. What does this state look like at a later time? For a conservative system, the state at a later time t is equal to a very similar superposition of eigenstates with the exponential times the infinite sum over eigenstates. The only difference is that now each eigenstate is multiplied by this term here, a phase factor that is proportional to the corresponding energy eigenvalue. In our case, the energy eigenvalues are those of the quantum harmonic oscillator. So we can rewrite the state at time t as equal to the exponential prefactor and then the sum over eigenstates, where I am including the explicit form of the energy eigenvalues of the quantum harmonic oscillator. The part of the exponent associated with its 1/2 here does not depend on n, so I can take it out of the sum, and then we have the usual prefactor, and then I am rearranging the remaining terms in the sum. Feel free to pause here for a moment if you want to cross-check this final step. So let's recap. If the initial state of the system is a coherent state here, then this here is the latest expression that we got for that state at a later time t. I'm now going to define the complex scalar alpha as equal to alpha 0 times e to the power of minus I omega t. It then follows that the absolute value squared of alpha is equal to the absolute value squared of alpha 0. Using this definition, we see that we can replace this term with alpha, and we can also replace this term here by the absolute value squared of alpha. This means that we can rewrite the state of the system at time t as equal to this phase, multiplying this exponential prefactor, and then multiplying the infinite sum over energy eigenstates. This whole expression now has the form of the coherent state alpha. And this means that we can write the state of the system at time t as equal to this phase factor times the coherent state alpha. And this is true for alpha equal to alpha 0 times the exponential of minus I omega t. Now, what does this mean? If the initial state of our system is a coherent state that is an eigenstate of the lowering operator with eigenvalue alpha 0, then the state of the system at a later time t is equal to this global phase factor times a new coherent state, which is an eigenstate alpha of the lowering operator, corresponding to eigenvalue alpha 0 times the exponential of minus I omega t. And remember that a global phase factor like this one here does not change the physics. This takes us to the key result relating to time dependence. A coherent state stays coherent at all times. Right, so this is it for coherent states. But before we finish, let's discuss one final thing. Given that coherent states are defined as the eigenstates of the lowering operator, a natural question to ask is, well, what are the eigenstates of the raising operator, A dagger? And it turns out that the raising operator has no eigenstates. To see this, let's write down a tentative eigenvalue equation for the raising operator, where I'm using lambda for the eigenvalues here, and also for the eigenstates here. Let's now consider the expansion of the eigenstate in the energy basis of the quantum harmonic oscillator, where as usual the expansion coefficients are given by this bracket. We now want to evaluate the eigenvalue equation for the raising operator using these results. To do so, let's start with the left-hand side, A dagger acting on the expanded eigenstate. We can move the raising operator inside the sum, and using the action of the raising operator on an energy eigenstate, which is equal to this prefactor, times an energy eigenstate with one additional energy quantum, we can then rewrite this term as equal to the infinite sum over Cn times the square root of n plus 1 times the energy eigenstate n plus 1. Going to the full eigenvalue equation up here, we can now write it in the energy basis as this left-hand side we just derived equal to the eigenvalue times the energy expansion of the eigenstate. Let's make some room. And let's copy the latest expression that we got for the eigenvalue equation of the raising operator in the energy basis. As the different energy eigenstates are orthogonal, then this equality will hold if the coefficients in front of each of the energy eigenstates match on both sides. So starting with the ground state, there is no ground state in the left-hand side, and the coefficient is lambda C0 in the right-hand side, so we get that C0 must equal 0. For the first excited state, we get C0 from the left-hand side, and lambda C1 for the right-hand side. As C0 is 0, then this implies that C1 is also 0. Repeating this argument for all terms, we get that for the nth excited state, the equation looks like this. And as the previous step showed that Cn-1 vanishes, this implies that Cn also vanishes. We therefore conclude that the eigenvalue equation for the raising operator will only be true if all expansion coefficients are 0. This implies that the only solution is one for which the eigenstate is equal to 0, and this means that the raising operator has no eigenstates. This result is actually relatively easy to understand conceptually. When we write any state lambda in the energy basis, then there will be an eigenstate in the expansion that will correspond to the lowest energy of all eigenstates. I will call this lowest energy eigenstate n-min. This may be the ground state itself or another state. When we apply the raising operator on lambda, then each eigenstate will turn into a new eigenstate with an additional quantum of energy. And this means that in A dagger lambda, the lowest energy eigenstate is n-min plus 1. This means that the lowest energy eigenstate in the new state will have one extra quantum of energy compared to the original one, so that the new state, A dagger lambda, can never be proportional to the original state lambda. This intuition confirms that there cannot be eigenstates of the rating operator. Note that these results are consistent with our discussion about the lowering operator, which does have eigenstates. They are the coherent states that we've been discussing today. This argument that we just put forward for the rating operator does not apply in that case, because a coherent state has no state with a highest energy, because the sum is infinite. And this is the reason that we have eigenstates of the lowering operator only. As a final comment, you may be worried that the rating operator has no eigenstates. But this is actually okay, because the rating operator is not a Hermitian operator. In summary, and in the context of the quantum harmonic oscillator, we've defined coherent states alpha as the eigenstates of the lowering operator. We've also found that we can write these coherent states in the energy basis as shown here, and the expansion includes all energy eigenstates. And finally, we've shown that if the initial state of our system is a coherent state, then the state of the system remains coherent at all later times. We now understand coherent states as the eigenstates of the lowering operator. But what makes coherent states interesting goes well beyond that. I encourage you to follow our series of videos on coherent states, in which we will explore, among other things, their relation to classical mechanics. Coherent states also play a fundamental role in quantum optics, for example, for our understanding of lasers. And as always, if you liked the video, please subscribe.